Thank you, Kim Young, and thanks to all the organizers of this wonderful school for inviting me to come here and give lectures. It's the third time I'm coming to the Asian Winter Schools. I was in Jeju a couple of years ago and in Zhuhai. So I was asked to give you an overview of developments in the last decade or so on trying to construct effective field theories of hydrodynamics. I apologize for the slides, but I feel I have too many long equations to make it worth my while to write it on the iPad. But hopefully I'll go slowly enough that you'll see you'll be able to catch up. The advantage, of course, is I'll make these slides available so you don't have to write down all the details as we go along. Okay, so a couple of basic things. So let me just get on with sort of the plan of the lectures. So there are a couple of things I want to do, and I've tried to organize them thematically across the 4 lectures between today and Friday. So today I'm going to basically review stuff that's in some sense ancient, but only got understood in the last few years, which is to basically review what people would traditionally call hydrodynamics and how it's formulated in some axiomatic way, tell you what the transport data are, and show how these axioms can actually be solved explicitly to tell you what kind of transport is allowed and what kind of transport is disallowed in traditional formulations. And I'll show you where some examples where these of systems where we can actually calculate and make these statements precise. Time permitting, I'll talk a little bit about fluctuations, although I'm skeptical that we'll get there today. Tomorrow I'm going to sort of switch gears and go back to a more fundamental quantum field theoretic perspective of saying, look, I don't care where this hydrodynamic effective field theory came from. There is some microscopic theory, some underlying quantum dynamics, and in that quantum dynamics somehow integrating out some irrelevant degrees of freedom should give us this hydrodynamic effective field theory. So how are we going to set up the rules? What are we supposed to compute? And why is this framework for hydrodynamic effective field theories different from what you might have learned in your standard quantum field theory courses, the Wilsonian RG, because there are the non-trivial subtleties which are not captured by the Wilsonian program. We'll see that there's a very nice way to sort of capture the basic data in terms of Schwinger-Keldysh path integrals, and how one needs to constrain some things which were called influence functionals in the literature or 50 years ago, and how much of this information can be very nicely encoded by passing on to some auxiliary BRST superspace which imposes constraints coming from microscopics into the macroscopic effective field theory. If I have time tomorrow, then I'll talk a little bit more about some things that people are much more interested in, which go beyond Schwinger-Keldysh, which is out of time ordered correlation functions that you might have heard of in the context of talking about chaos and thermalization, etc. The third lecture I'm going to apologize is going to be quite technical, where we are going to try to take this data and put it together in some useful form, but that unfortunately will require us to go through some mechanics of BRST superalgebra and constructing multiplets. So these are not in some sense standard multiplets, so we're going to have to do a bit of work. It's well known in certain contexts, but I'm sure most of you who've sort of studied supersymmetric field theories haven't come across these multiplets in your traditional presentations. The mechanics, once you understand it, is not going to be that different from n=1 supersymmetry in 4 dimensions, but there's some useful ways of parameterizing these multiplets that we will sort of go through in some detail. And once we have that, given these constraints and the background knowledge, we'll easily write down the effective actions for hydrodynamics consistent with these axioms. And the last lecture is basically exploring how that's going to happen. Okay. So there's a lot of literature on the subject, and I've captured for you here the series of papers that I have been involved in and some others have been involved in, which tell you what's going to happen. That they're sort of roughly categorized by lecture. So this is what I'm going to use today. This is what I'll use tomorrow. And there's more details by other groups and ourselves in constructing effective actions, which we'll use in the following 2 lectures. Okay, so that's about the logistics. So without further ado, let's get started. There's some background material that I would recommend you to look at if you're interested in some of the details of what I'm going to say. So these are, of course, explained in a particular context of hydrodynamics in the papers aforementioned, but there's a lot of stuff that happened much before we got into the subject, in particular in the context of hydrodynamics by various groups in topological field theories dating back to the late 80s and early 90s, and even more earlier in the context of stochastic and statistical dynamics by various folks, and I'll bring in these concepts in due course. But these are some of the seminal papers that I have found useful in understanding what's going on, so I recommend them to you. Okay, so let's get started. So what do we mean by hydrodynamics, and what kind of effective field theory are we after? So I'll say at the outset that I'm only going to talk about relativistic hydrodynamics. The standard story that you might hear when you think about Navier-Stokes equations is for incompressible non-relativistic fluids. I could say many things I'm going to say for incompressible non-relativistic fluids. There's a catch, however, that the Galilean invariance that governs incompressible non-relativistic fluids is not as powerful as Lorentz invariance. So the structures I want and the structures I want to classify are much simpler if I assume Lorentz invariance. We should be able to do everything I'm saying for the non-relativistic case. It's just that it's a harder job. For example, if you just think about what data I need to tell you for how energy and momentum transport happens in a hydrodynamic system, there's only one energy momentum tensor I need to prescribe for you in a relativistic field theory. In a non-relativistic field theory, energy and momentum are not correlated. They're just because space and time are not correlated. Okay? So what I need to tell you is independent data for a shear stress tensor, an independent data for an energy flux vector, and an independent piece of data for the momentum flux vector, and they all transform differently under the Galilean group, which makes the problem of classifying structures that show up a bit more complicated. It can be done, and various groups have started thinking about this in the framework of what's the right geometric language to think about non-relativistic physics, which is the Newton-Cartan geometry. But that's something I'm just going to avoid for sake of simplicity. So with that caveat, so imagine you have some physical system, some relativistic field theory. It could be your favorite quantum field theory, be it QCD, be it N equals for super-Yang-Mills, what have you. And what you're asking is the following question. I take this relativistic field theory, it's interacting, and I want to take this field theory at some finite temperature, but I want to ask the question, so if I take the field theory at finite temperature and assume that and let's say for simplicity, temperature is uniform everywhere, so that I'm in some kind of global equilibrium, we can basically do thermodynamics. We can just compute some free energies, we can ask what the energy is, what the pressure is, and so on and so forth. But what I'm after is a situation where I'm in some kind of local equilibrium, but not in global equilibrium. Okay, my system is not homogeneously thermal everywhere. It's a bit like this room. It's slightly draftier outside, it's warmer out here, and there's a sort of flux of heat coming in from inside to outside, and so on. So there's some local equilibrium, and we'd like to ask, how do you quantify and characterize this local equilibrium? Because you also not only want to characterize what's happening here, what kind of local temperature there is, but also what the flux vector is going from outside to inside. So in order for us to make sense of this, we could ask this in many contexts. You could ask this in the context where you take a room and you put a radiator and see how the heat flows out from the radiator. Now, of course, there'll be lots of transients as you switch on the radiator and the room starts warming up. But what you're after is the question of what happens when things have sort of settled down, but it's not the sort of transient modes that are governing the physics, but the sort of modes that are, in some sense, the Goldstone modes that characterize the long time behavior. That's what every effective field theory is after, and the hydrodynamic effective field theory is similarly after questions when you ask for departures from equilibrium that happen on reasonably long spatial temporal scales, so that it makes sense for you to think of reasonably big domains where you can use thermodynamic intuition, and these reasonably big domains sort of talk to each other, exchanging energy and momentum flux. Okay? So that's the kind of cartoon that I've tried to draw here, that you have some domains where you have local pieces of energy and momentum that are sort of roughly color coded. I'm not sure you can see it. And these local domains that if you sort of bring a thermometer and ask what's happening here, you can locally measure what the temperature is, and it's roughly constant. But the temperature is not truly constant across this whole fluid. It's changing from here to here, but the rate of change is sort of slow in this region, so you can approximate it by a local domain of equilibrium. What's actually happening is that there's some kind of exchange of data, exchange of energy and momentum from one domain to another, and that you have to characterize by some flux vector. Okay? So we'll parameterize these data, and then we'll ask how are we going to sort of write down this in some effective field theory form. What are the objects? What variables should we talk about? And how do we systematically understand the departure from equilibrium? So in equilibrium, this whole thing will be a homogeneous color, and there will be no flux of anything because the temperature is uniform, energy densities and pressures are uniform everywhere. So the main thing we want to talk about is some kind of mean free path. So if you sort of the canonical way to think about this problem is to think about this problem in the example I just mentioned, where you have the room and air molecules, and there you can think of the sort of local mean free path of this air molecule. The air molecules are sort of freely moving around, and they sort of meet each other and collide, and the sort of length scales between collisions, the time scales between collisions set the mean free scale, and you want this mean free scale to be small compared to all the variational scales in the problem. So you want sort of temperatures and other charges to vary, but on scales much larger than the mean free scales. Now this picture of course makes perfect sense for this non-relativistic problem of air in this room, where you can talk about free particles with some collisions after some time. This may not happen if you have some strongly interacting quantum system. And what we want is a framework that we can just talk about any system independent of what the coupling constants are. Okay? And in particular, what I'm going to try to do is I'm never going to calculate the actual coupling constant dependence of various parameters that enter hydrodynamics, but rather explore what their structural properties are. I'll show you some computations toward the end of today's lecture of where people have computed them, but rest assured that some of the things I'm going to tell you are much easier to compute in strong coupling, where you can use some tricks from holography, than in weak coupling. Okay, so let's recap. Hydrodynamics is going to be for us the theory of low energy near equilibrium fluctuations, where you start from a system that's initially prepared in a thermal state in some thermal Gibbs density matrix, except that you're going to allow this Gibbs density matrix to be inhomogeneous in space and time, and there will be sort of departures from equilibrium that are large on scales characterized by some mean free path. So when you have such a system, we should ask ourselves, what are we supposed to keep track of? We want some effective field theory, so we don't want to keep track of all the detailed physics that's going on in the microscopic description. We may not be able to keep track of the detailed physics that's going on in the microscopic description, especially if we're talking about some strongly coupled soup of particles that, for example, one system that you can keep in mind is the quark-gluon plasma, which is formed by sort of colliding heavy ions and exists for a time scale of order of few femtoseconds before it hadronizes. In that quark-gluon plasma, there's some local regime where things behave in a hydrodynamic fashion. We know this empirically. And you'd like to ask, how do you characterize that system? You cannot keep track of the individual data of what each of the constituents of the heavy ions are doing, nor can you go down all the way to QCD and keep track of what all the quarks and gluons are doing. What you want to keep track of is what the macroscopic variables are and how do you characterize them. For our problem, the macroscopic variables are going to be the conserved charges that characterize how energies, charges, and momenta flow across the system. There will be one special case, there will be one special object that I'll introduce, and that will be this entropy current. Okay, since we are relativistic, energy and momentum are captured in one object, the energy momentum tensor, and that's a key simplification, as I said, from the Galilean case. There's a charge vector that tells me how charges behave, and this entropy current is something I'll introduce in a second. These currents are what we want to keep track of. In a quantum field theoretic sense, what we're after is the expectation values of these objects as of in the near equilibrium Gibbs state that we are studying. How are we going to characterize these charges? Here, for now, we are going to basically use the intuition that these objects should be characterized by exploiting the fact that we have local equilibrium. So we should just talk about the local features of equilibrium in each domain and express these objects in terms of those. What would those be? Well, if I said I have a density matrix which is nearly thermal, then locally I just need to tell you what the intensive parameters describing the density matrix are. They'll be things like temperature. There could be things like chemical potential if I have charges. So if you have some non-abelian symmetry algebra, some global symmetry, then these chemical potentials will just be elements of the Cartan of that symmetry algebra. In everything I write, I'll mostly write a single chemical potential. We can generalize easily to multiple chemical potential. And as we go along, since it will get more and more complicated to keep track of chemical potentials, I'll even drop chemical potentials and talk about neutral fluids. Okay? But some of the references I've listed before explain how to extend everything I'm going to say to charged fluids. But we also said that these temperatures and chemical potentials are not homogeneous, so there's a flux of energy and momentum across these domains, and that flux vector is characterized by a velocity vector, which you physically think of as a fluid velocity. So this fluid velocity is roughly telling you how things are being propagated across this fluid, and since it's measuring something propagating, it's a time-like vector, and without loss of generality, you can normalize this time-like vector to have unit time-like norm. Since we're talking about conserved currents, the simplest way to extract conserved currents is to couple them to external sources. Okay, so of course we are eventually interested in fluids that are propagating in maybe flat space-time with no chemical potentials. You don't have an external battery that's sort of driving the fluid flow. But in order to access them, it's much simpler to imagine that your fluid is propagating in some curved space-time with some metric g mu nu and has some background gauge field, flavor gauge field a mu, which in turn couple to t mu nu and j mu respectively. Okay? So in other words, eventually when we talk about quantum effective actions, the energy momentum tensor will just be obtained by taking this effective action and varying it with respect to the matrix as usual. And likewise for the charge current. Okay? So everything here is straightforward. In this slide is reasonably standard, except for this one object, which is the entropy current. For now, let's continue to parameterize and then come back to this entropy current. It's actually useful. So most traditional formulations of hydrodynamics will just work with those variables I gave you, but it turns out to be a bit more helpful to repackage them a little bit, and you'll see why as we go along through the rest of this lecture. So for now, just pretend that I sort of happen to know something that you don't, and I'm going to sort of capture this set of variables, the temperature, the chemical potential, and the velocity. I'm just going to repackage them by a field redefinition. So I'm going to define a vector beta, which is the velocity vector divided by temperature. So the velocity vector was normalized. Beta vector its norm will give you the temperature. It also will be a time-like vector, and I'm going to call it a thermal vector. If you have chemical potentials, you can sort of take the chemical potential divided by temperature and then subtract a piece of the gauge field from it, and we'll call it the thermal twist. It's called the thermal twist because it really, if you think of the Euclidean formulation of thermodynamics, it's a twist, it's a sort of twisted boundary condition the charge fields obey as you go around the thermal circle. So the data we have is the following. We have these fields, which are the background fields, and the physical fields, the temperature and velocity combined into beta, and the chemical potential combined into lambda beta. We have the physical currents, one of which I have not explained to you, and all we are after is an expression for these currents as a functional of these fields. Okay? That's to 0th order what you have to do, and at some level it sounds like a very easy problem. Well, I have a vector, a scalar, a 2 tensor under one form, and you just have to describe a symmetric 2 tensor, which is energy momentum current and the charge current in terms of those. You say, how hard can this be? Just write them down and construct them, if you want, in some effective field theory language, construct them order by order in derivatives, right? Because you can think of derivatives associated with this background metric acting on various fields, and you can expand, you can write down a space of symmetric 2 tensors built out of objects from these guys. So if that was hydrodynamics, life would be very simple. There's no reason to give this set of lectures. So we'll see what the problem is, and the problem has to do with this entropy current vector, which I have not yet defined for you. Yeah.
Beta of lambda is not index.
No, the beta on lambda is not an index. Lambda is a scalar object. Yeah. As you can see, it's basically a chemical potential redefined, and so it's just a pure scalar under Lorentz transformations. Okay. So before I do that, let me tell you some more. Why this is actually a simple theory. It's a simple theory because conserved currents are by definition conserved up to work terms. Okay? So the dynamics of this system is very, very straightforward. There's not much happening except that energy momentum tensor would be conserved, except when you have external background gauge fields, in which case you have a Lorentz Joule heating term, which does work on the system. So current times background gauge field strength gives you, it's like E dot J0 term. And I've also added here some additional pieces with these perps on them, which signify that I assumed that my flavor symmetry was not anomalous. I don't have to do that. It could be that my flavor symmetry is anomalous, in which case the conservation of current is broken by the anomaly term. So if, for example, if you have just think of the current conservation equation, if you had a non-anomalous flavor symmetry, the divergence of the current would be 0. But if you have an anomalous flavor symmetry, when you have background electric and magnetic fields, the divergence of the current would be in 4 dimensions, would have an E dot B term on the right hand side, the standard Adler-Bell-Jacob anomaly term. Now, the reason by and large, I'm not going to talk about anomalies in these lectures, but at least in the beginning, I want to emphasize this, because much of what happened in the last decade in terms of trying to understand hydrodynamics owes to a discovery that anomalies that you usually study in quantum field theory at 0 temperature leave a non-trivial imprint, and perhaps calculable and quantifiable, not just calculable, but perhaps measurable imprint in finite temperature field theory. Okay, so this is a very interesting subject in its own right, and I won't be able to do justice to it, I'm sorry, but I encourage you to look at various pieces of literature that have discussed this in the last 10 odd years. There are many ways to think about these two equations. You could just think about them as dynamical equations for the low energy effective field theory, or you can think of them as word identities for the 1-point functions of conserved currents in this fluctuating Gibbs density matrix. So you prepare your state in some Gibbs density matrix, you're sort of asking what are the effective quantum stress tensor and quantum charge current, and they will satisfy these word identities if you turn on background sources. Okay? I'd like to pause here to ask if people are happy with this discussion, because this is going to be crucial as we go along. So if people have questions about what I've said so far, please ask. Okay, great. So our task is to try to give expressions for this energy momentum tensor and charge current consistent with this dynamics, which turns out is not hard to do. You could do what I just said, just write down the tensor structures and go to town with them. And in some sense, that's sort of a very easy exercise because it's just a classification of tensors. It's not, there's not very much physics to it. But there's a piece of physics that's very important, which is that this is not an unconstrained system. Okay? The system has a non-trivial constraint, and the non-trivial constraint is the following. Microscopically, your theory, which could be QCD or which could be R equals 4 SOP Yang or something else, is time reversal invariant. Macroscopically, it's not. Why? One has to demand that macroscopically, whatever energy momentum tensor and charge currents you write down, they have to be consistent, and the dynamics for them has to be consistent with the upholding of a second law of thermodynamics, not in the global form, not by saying that entropy is produced, but in a local form, because they're talking about local effective field theory. In the local form, by saying that there has to be some current which has no microscopic origin, because microscopically things are time reversal invariant, a current which is this entropy current, this mysterious object, which is locally non-negative definite divergence. Okay? This current a priori has no origins in a Noether construction because it has no associated charges. Okay? Energy momentum comes from diffeomorphism symmetry. The flavor current comes from flavor symmetry. This guy is postulated as a consequence, as a constraint on the macroscopic effective field theory, and this is something we know empirically to be true, and the goal of these lectures, towards the end at least, will be to explain where this comes from. But for now, we're going to take this as a given, as one of our axioms, as in fact the primary axiom of hydrodynamics, and ask, how do we understand the construction of hydrodynamic stress tensors and charge currents consistent with this statement? This statement complicates life significantly. Okay, so that's what I just said. So if this statement was not there, life would be very straightforward. You could just do representation theory by just classifying tensors of various kinds. The trouble with this is the following. What this statement really means is that in every physical fluid configuration, when the fluid flows, entropy must increase. Okay? This statement must be true locally. But you see, when I say when the fluid flows, it means I have solved the fluid equation of motion. It means I'm not just classifying off-shell structures of energy momentum and charge currents, I'm actually having to solve the equation of motion. And anybody who spent any amount of time trying to solve non-trivial flow equations for hydrodynamics knows that they are wretched, complicated, hard PDEs. So, imposing this on shell is not an easy task. Yes, you had a question.
So no symmetry associated with them?
For now, no. By the end of the 4 lectures, yes.
Or is it broken?
You will see where it comes from, but for now, for now, this is just a statement about how you would see this presented in standard discussions. So much of what I'm going to tell you is demystifying the statement. So for today, I'm going to explain what the statement implies, and the next 3 lectures, I'm going to build up machinery to demystify it. Thank you. Now, there are many subtleties with this. In particular, there's nothing unique about this current. I mean, there's something physically meaningful about the energy momentum tensor. You can measure it. You can sort of take your system, subject it to some gravitational potential, and measure what the energy momentum response you get is. But this statement just means that, somehow you should be able to write down some vector current which has non-negative definite divergence on every fluid flow. There's no statement of uniqueness, you just need some entropy current. And as I just remarked, a priori it's mysterious, it doesn't seem to associate any symmetry per se. Okay? So this I think is at least for us was an important challenge, because here's an example of something where the Wilsonian paradigm would not work. The Wilsonian paradigm does some coarse graining, but doesn't generate entropy in the standard way of thinking about it. So how do you understand Wilsonian hydrodynamic theory consistent with the second law? And that's roughly what drove us and other people to construct these effective field theories of hydrodynamics. Okay? For now, I'm going to sort of let that question aside and try to explain to you, given these constraints, what can we say about hydrodynamic transport? Okay? And for that, I'm going to sort of build intuition step by step and give you a classification theorem for what is allowed and what is not allowed, consistent with what's here on this slide. Any other questions? Yeah?
I think in classical fluid mechanics,
Yeah.
For example, if you have a Boltzmann equation, which can be formulated with a microscopic Hamiltonian,
Correct.
and we have a standard procedure of obtaining the Navier-Stokes equation from the Boltzmann equation,
Yeah.
then probably the procedure must explain the first statement.
It does, yes. That's the Boltzmann H theorem.
Yes. So
Yeah.
then you must get clue from the derivation.
Yeah. So
of
you.
the mysterious point.
Yeah, you partly get a clue, but not enough, and I'll tell you why. So first of all, my biggest complaint with that derivation is that it assumes a quasi-particle picture. It assumes that there's some kind of free streaming behavior until collisions happen, and that's not necessarily true in strongly interacting systems. So there's several other corollaries to it, and many things I'm going to say should be re-understood in that language, something that we and others haven't done, but I think can be done very easily, because it's a very well-established set of results that exist in the literature in that context. But for now, let's just say that in that case you understand this to some extent, but you'd like to understand this very generally by some symmetry principle, something that could be as nice as the Wilsonian paradigm that you just look at it and say this is all you can do. Okay, so you'll see consistency with what you know from the Boltzmann equation, but for now I'm not going to use that intuition. And turns out you don't need to use that intuition, so we'll see how far we can go.
In the experiment,
Yeah.
how can you measure this entropy current?
I don't think it's a measurable quantity. Okay, it has measurable consequences, and I'll explain the measurable consequences in a second, but I don't think the entropy current is something that you're going to be able to measure. It's a similar question you could ask Tatsuma tomorrow when he introduces von Neumann entropy. How do you measure von Neumann entropy? So it's a coarse-grained version of von Neumann entropy, what I'm going to talk about. Okay, yeah?
what if it has some entropy production?
Sorry?
What if there exists some entropy production, not just the entropy flow?
What happens if there's entropy production? Well, the entropy flow will induce entropy production. I'm just saying that the way hydrodynamic axioms are formulated, they're formulated more strongly than necessary. You could have just said the total entropy is produced and the total amount of entropy that is produced is positive. That would have been what you would learn in the standard second law of thermodynamics. Okay? The total amount of delta S, where S it's S final minus S initial, is bigger than or equal to 0. Okay? I'm saying something stronger. There has to be a local current from which that follows. Okay? So that's not a priori required, but it's a priori imposed on hydrodynamic effective field theories.
To construct the local form of second law thermodynamics.
Yeah.
Is it sufficient to only impose on shear condition?
It is sufficient. Yeah. The local form, at least as it's formulated, is predicated upon that local form holding on shell. Okay? So going off shell, of course, you're not imposing the equation of motion, so it's much weaker. So in fact, that's what I'm going to do. I'm going to take the statement of entropy production off shell, because then life is a lot simpler. Before I do that, let me just give you some picture of and establish some notation for what we need. So I'll by and large talk about neutral fluids, as I said, because it's easier to just write variables for them. For the charged fluids, there are a lot more variables and a lot more fields. So a neutral fluid, of course, just characterized by the energy momentum stress tensor. And let's just see what we can do to the first few orders. So let's imagine we didn't worry about the entropy production for a moment. And so we have, since it's a neutral fluid, I just have this beta vector and a metric. I'll write here the answer in standard parameterization. You can of course rewrite it in terms of the beta vector by just rescaling. So a symmetric 2 tensor with no derivatives has two tensor structures, one which is composed of this bivector UU, and the other which is built out of this projector P mu nu, which is G plus UU. Remember, U is a time lag vector, so G plus UU is a purely spatial metric. So the way to think about P mu nu is that it's a metric on space after you've sort of thrown out the time direction in terms of U. Okay, so think of P as a spatial metric. And that's the only two symmetric objects we have with no derivatives. And they can be multiplied by independent functions of temperature, which you would usually call the energy density and the pressure, because the energy density is what you measure by sort of looking in the time component of the energy momentum tensor, and the pressure is what lies along the diagonal of the spatial piece of the energy momentum tensor. If you go to one higher order with one derivative, well, you can take the derivative of the velocity. You can decompose the derivative of the velocity into a symmetric piece with a trace removed, a pure trace piece, an antisymmetric piece, and a transverse vector piece where the vector is transverse to the time-like velocity direction. Okay, so that's a general decomposition for any gradient with a specified direction. And I'm going to give these four things names. The symmetric traceless piece is called the shear, the antisymmetric piece is called vorticity, the trace is called the expansion, and the transverse vector is called acceleration. Okay? And should I need it, you can think of this kind of object, this combination of tensors, which shows up in this, for example, in the construction of shear, as a symmetrization with trace removal in one shot. Okay? Instead of using usual parentheses for symmetrization, you can also use these brackets to just remove the trace. Okay, so I've written two terms here, and you might ask, there's one more term I could have written down, which is the gradient of temperature itself. So I can write down gradient of temperature times gradient of temperature. That's also a gradient of temperature times velocity, which is also one derivative object that could have come with its own coefficient. It would in a non-relativistic case, because that's what would tell you what the heat current does. Okay, that's what would tell you what the thermal conductivity is. In a relativistic theory, you can remove it by a field redefinition, because there's no independent distinction between energy momentum transport and heat transport. Okay, anything that transports heat also transports energy and momentum. Now, these guys have names. Eta, which multiplies the shear tensor, is called the shear viscosity, and zeta, which multiplies the expansion, is called the bulk viscosity. Okay, so this is what we get without doing any work, right? Because we're just classifying tensors. But now we can put in the work. We can ask what happens by demanding the existence of an entropy current vector. Here's what happens. You'll find that there's going to be some constraint on energy and pressure. In particular, there's going to be a constraint that the energy and pressure are derived from the same underlying free energy term. satisfying thermodynamics. There's going to be a constraint which says that these coefficients that multiply the shear tensor and the expansion are non-negative definite. So in particular, you have positive values of shear and bulk viscosity, which is the statement that the fluid actively likes to relax back to equilibrium. It doesn't like to run away from equilibrium. Okay? That is, the system physically has friction, it doesn't have anti-friction, and that's this statement. But the way the statement arises is from demanding the existence of this entropy current. Okay? So I'll explain that in more detail as we go along. But that's the upshot, and at this order, it turns out that the entropy current itself is just the entropy density, the thermodynamic entropy density, times the velocity vector. Okay? So this slide is actually accurate and complete to first order in derivatives for neutral fluids. This is completely all the data and all the constraints that you can have. As I promised you, I am not going to tell you what the individual values of eta and zeta are. They are non-trivial functions of temperature, and they depend on what physical system you're talking about. So you could be talking about the quark-gluon plasma, for which people believe that zeta is very small, not quite zero, but getting close to zero, and eta is very small and bounded by, and in fact almost entropy density in units of, or divided by 4 pi, in units of h bar, kb and h bar. Okay? Then, just to go back to something that was said earlier, suppose you were doing this in kinetic theory, we were doing Boltzmann equation, so which is basically perturbation theory around some weak coupling point, then rather counterintuitively eta is large and zeta is large. It's counterintuitive because you might think that a free theory has a lot of friction, but it doesn't, simply because in a free theory, in an explicitly free field theory, there is nothing to relax the system away from equilibrium. There are no interactions, particles are just free streaming, they don't talk to each other. So the only way they will start talking to each other is when you sort of switch on the infinitesimal coupling, and then you'll find that eta diverges like 1 over lambda log lambda in perturbation theory. So it's actually a non-trivial calculation to compute eta in perturbative 5 to the 4 theory, for example, a task that was only accomplished about 20 years ago after a lot of work and a lot of resummation of thermal field theory diagrams. In contrast, turns out that they are much easier to compute in strong coupling if you can talk about holographic systems, because the calculation is pretty much back of the envelope if you know what you're doing. Okay, so that's a preview. What I want to do now is I want to give you some intuition of how one might take those constraints that I wrote, take the hydrodynamic description I gave you in terms of these axioms, and just basically classify, just as I did in the previous slide. So the stuff I showed you on the previous slide is very, very well known. You can go and read about it in Landau-Lifshitz textbook on fluid mechanics. It's ancient and venerable. But if you want to go to higher orders, you might say just run the procedure. And as you can imagine, as you run the procedure to higher and higher orders, which is what people did initially, it starts getting more and more complicated. And so what I'm going to try to do is give you a picture of how you might sort of not do this step by step, case by case, order by order, but just solve the whole thing at one fell swoop. Okay? And that will result in a classification system, and it will tell us what is allowed and what is disallowed, and what are the constraints on things like transport data, like shear and bulk viscosity, at any given order in the hydrodynamic expansion. Okay? The reason to do this is the following. What you would have done at the end of that is you would have completely specified for yourself what are the allowed structures of energy momentum and charges in a hydrodynamic expansion consistent with the local form of the second law. Then you can go and ask, suppose you are trying to derive this from some microscopic picture. How would you get those on the nose? Okay? So in some sense, this gives us a nice benchmarking scheme to sort of set the stage so we know what we're shooting for when we're starting to shoot in the dark. Okay? And the way we're going to do this is in 3 steps. So today what I'm going to show you is how you would take this entropy current constraint of shell, which is actually quite a simple statement, and then once you've done that, it then becomes an exercise in cleverly thinking about tensor algebra to classify all allowed constitutive relations. So I didn't quite explain this, but so let me just say it here. This expression for the energy momentum tensor as a functional of the fluid data, the velocities and temperatures and the background sources, this is called constitutive relations, and the undetermined data are these coupling like parameters, the shear and bulk viscosity and transport coefficients, etc. Okay, so I'm going to do that, and then the remainder of this lecture series is going to be devoted to getting them from an effective action by sort of going back to the microscopics and asking what are we going to do there. Questions?
So the JS is just a non-relativistic nature.
Sorry?
We cannot see that from relativistic fields.
What can we not see?
The JS, the entropy.
No, you can. Actually, okay, let me tell you a dirty trick. It's not going to be universal. It won't give you everything. There's a very easy way to get from the non-relativistic theory a non-relativistic fluid. In particular, non-relativistic incompressible fluid is very, very easy to get from the relativistic case. How would you do it? Okay, so let's think about physically what's happening in a fluid. In a physical fluid, you have sound modes, okay, phonons propagating, which are basically energy density fluctuations. And on top of that, your momentum diffusion, because it's a fluid system, so it has a diffusive piece to it, and momentum diffuses. Okay? Now, momentum corresponds to spatial diffusion, and energy sound modes correspond to temporal variations. So if you want to go to the non-relativistic limit, basically what you want to do is allow sound to propagate through the system, homogenize energy densities, and then focus on the subsonic, lower frequency, lower energy diffusive modes. Diffusion is a much slower process because so sound is of course propagates slower than light in physical media. So, but shear diffuses even slower. Okay. So it's a very easy way. All you need to do, so technically all you would need to do is you take a system, take my equations, and scale time twice as fast as space. Okay, which is the non-relativistic scaling. It roughly speaking sends speed of light to infinity, and you get the Galilean invariant system. So leave it as an exercise. You can take the expression I wrote previously, write down the conservation equation, and see that if you take my limit, you'll get the Navier-Stokes equation. It's a bit more trickier to get the compressible case, because in my limit there's no energy. The system is completely incompressible because energy is homogenized. So for compressible fluids, you want to also allow for some local density fluctuations. Okay. Okay. So let's then get started by trying to take the entropy current off shell. Okay. So let's recall that what we want is a current J mu S whose divergence is locally non-negative definite. I'm going to call that amount of divergence delta. Okay, just instead of keeping it written every time, I'm just going to call it delta, and delta is required to be positive definite. And this is going to be physically being why is it produced? It's physically produced because the system has friction, and dissipation is what's causing entropy production. Now we can play a trick, and we can play the following trick. You can take this equation and you can add to it the dynamical equations of motion that I had before. What were the dynamical equations? They were energy momentum conservations. I've brought to the same side the work term and the anomaly term, and likewise the current conservation equation. So this is a vector equation This is a scalar equation. I could add to my entropy production equation a vector equation with a vector Lagrange multiplier, and I could add the scalar equation with a scalar Lagrange multiplier. Right? So I can do this, and I would have some Lagrange multipliers, and I'll tell you why I've chosen these particular Lagrange multipliers in a second. And if I did that, then on shell, these terms would be 0, and but if I'm not imposing the on shell condition, and on shell these terms would be 0, and of course I'll be back to my previous equation which requires that on shell I have energy entropy being produced correctly. What you can do is you can actually now think of this equation as the off shell version, but you still have two Lagrange multipliers to play with, a vector and a scalar. And here something nice, there's something you can do which is very nice, which is that there's no fixed reference frame which says what you mean by a local velocity and local charges, what your local chemical potentials are. Because you go to a system which is some fluid, and you try to look at it in your inertial frame and ask what temperature you are measuring. Okay? So you can make a choice of reference frame, which in this case amounts to a choice of a field redefinition for what you mean by velocities and temperatures. And exploiting these field redefinitions, you can fix these Lagrange multipliers to be precisely the hydrodynamic variables. So the vector Lagrange multiplier by field redefinition can be brought back to the form of the thermal vector, which is the velocity divided by temperature, and the chemical potential which is encoded in this thermal twist becomes the scalar Lagrange multiplier multiplying the charge conservation equation. And it's a statement that I'll just assert for now, but you can prove this, that this statement can now be viewed as an off-shell statement for entropy production, and solving this statement off-shell is equivalent to classifying all possible forms of transport. Okay? And there's a very nice feature about doing this way, which is the following. What you have here is some functional equation for various currents which you need to determine. So T mu nu is something you don't know, J mu s is something you don't know, and J mu is something you don't know, and you want to determine them as functionals of beta vector, the chemical potential, and background sources. But that you can do by solving this functional equation order by order in gradients. In fact, you can do even better. You can do this by first thinking of this as an inhomogeneous equation with a non-trivial source term delta on the right hand side. You can solve it by asking for all solutions which guarantee delta is non-zero and positive, and then separately solving the homogeneous piece which sets this whole thing to 0. Okay? So I'm going to do that, and that motivates a very nice way of thinking about hydrodynamic transport in two distinct pieces. One which leads to entropy production, which is of course has to be dissipative, so I'm going to call it dissipative or class D. But then it will turn out, and this was a surprise to us, some elements of this were known, but I don't think structurally it was very clear a priori that this is going to happen, that there's a lot of transport that is not dissipative. A lot of transport that's what we call adiabatic, because it leads to non-trivial flow of energy and momentum, and perhaps even non-trivial entropy current, but no entropy production. Okay? So this is the first key thing I want you to know, that there is the sort of the things that you know of, which are things like viscosities and conductivities, which lead to entropy production, because they allow the system to relax back to equilibrium. But there's lots of stuff that leads to no entropy production, but nevertheless leads to non-trivial forms of transport. Okay? Yeah?
Can you add some higher order of equation motion?
You could, but you just make your life more miserable because that would make this much more nonlinear than it already is. Yeah. One could, but it turns out this, I mean, so the question is what do you need to do to make it sufficient? And this was sufficient. And okay, we didn't discover it this way. But let me tell you certain statements that are true. This statement can be then derived in some other ways of thinking about it as the Bianchi identity, which means that this is implied by some other symmetry principle. And going back to a question that was asked earlier, that will enable us to explain where entropy comes from. Okay, so there will be some statement of that kind by the end of my lectures. Okay, so these kind of structures are, well, maybe there's a one sort of post facto evidence which sort of corroborates what I just said. These guys, T mu nu and J mu, are one variation with respect to background sources. Okay, so and that's why this equation is linear in them. Similarly, you want to add to them to this guy. So I can't justify this because this is not how we thought about it a priori, but it's just true. This guy also comes from some variation of something, okay, something mysterious which I'm not telling you yet. So since it comes from some variation of something, they better all come at the same order, and you don't make things any more nonlinear than they are. So post facto justification, but I think that's the right way of thinking about it. Any other questions? I hope this is clear. So what we're going to do for the rest of the lecture is just solve this equation. It's turns out to be a very easy equation to solve, and as far as I can tell, could have been done 50 years ago. It wasn't. So okay, let me do a little bit of repackaging, which makes it even more easier to solve. So let me split this. Let me take the entropy current and split it into two pieces. One which looks like a piece built out of energy, momentum, and charges. And in hydrodynamics language, this has a meaning. It's usually what's called the canonical form of the entropy current. If you're wondering where this comes from, if you think of the time, the 0 component of this, J0 sigma equals 0 component of this time component of this current, that would be entropy density times some in the time direction. Beta times T would tell you then roughly what the energy is divided by temperature. And this will tell you some charges, so this is like, and N0 would then be like free energy, just the equation that says, the usual equation which says free energy is energy minus T times S. Okay? So N, which I'm defining here, is the piece that's non-trivial piece of the energy, of the entropy current. And by virtue of what I just said, it's a free energy current. Okay? It's a free energy current normalized by temperature, but N is nicer to work with, so I'll keep it as N. And if you're wondering why N, you'll see later on that we'll call it N because it's going to be a Noether current for some symmetry. Now, if you just take this definition and plug it back into this equation, you'll see that the derivatives will hit in the J mu S, will hit this T and hit this J, and those terms will cancel with these terms, and the remainder pieces is where the derivatives will hit the beta vector in here, and all you end up with after some remassaging is this equation. Okay? So if you didn't have anomalies, you could forget about this n perp term. It would just say that the divergence of the free energy current is related to the energy momentum tensor dotted with some structure, and the charge current dotted with some other structure, and these structures are nothing but the Lie derivatives, the gradients of beta vector and the derivatives of the background potentials, which I've rewritten as Lie derivatives for simplicity. Okay? And you'll see why I've written them as Lie derivatives in 5 minutes. A good way to think about this is that delta beta G mu nu is nothing but a diffeomorphism on the background metric treated as a background source. We are not doing dynamical gravity, remember. Metric is just something we're putting in to probe how the fluid is responding to energy momentum. And the symmetrized derivative over one form is of course the Lie derivative, and what this piece is telling us is that if you make a diffeomorphism along the thermal vector and a diffeomorphism plus gauge transformation along the thermal vector and thermal twist, these are the two pieces you pick up. Okay? So this equation has some nice features. It has the free energy current that we need to determine. It has no derivatives acting on the conserved currents we need to determine. That's already nice, because you can start postulating structures for them and seeing how to simplify them. It has geometric pieces coming from background sources in terms of the physical fields. And then there is entropy production. Okay? The key fact we're going to exploit is the following. We're going to order things. We wanted to order things derivative by derivative. Okay? We might as well order things by del B. So del B is some variation of background sources by our physical fluid variables, which is the thermal vector and thermal twist. What we are going to do is we are going to think of gradients as powers of del B. Okay? And the reason to do this is that in equilibrium, del B will give you 0. So departures from equilibrium are measured by how much del B you have. And the more departures you have, the higher gradients, the more powers of del B you will get. And so classification of the full structure is a problem which is organized order by order in powers of del B. Okay? Or in powers of these diffeomorphism and flavor gauge transformations. And that turns out to be a very easy exercise to do, and I'll show you in the remaining bit of time for the day, 15 minutes, how this was done. Okay? But let me tell you the answer. So it turns out that there are 8 distinct classes of solutions to those equations, and this classification doesn't make any use of CPT properties. Other groups in the recent past have argued that maybe you can refine this classification using CPT properties. I'm not going to go into that. I'll point you to literature if you're interested. So there will be the sort of obvious dissipative class that I talked about, the thing that produces entropy, that will give you non-zero delta. It turns out that the space of solutions where delta equals 0 to this equation, so I'm going to call this equation the adiabaticity equation, and the space of solutions to this equation with delta is set to 0 is actually quite large. It's 7 distinct space classes of solutions. There's one which is easy to sort of take care of at the beginning, is basically what shows up when you have flavor and Lorentz anomalies. So that's the anomaly induced transport in this piece. So let's get rid of that, and that even if you get rid of that, there are 6 distinct classes. There are things which won't make any sense to you until I tell you what they are, and then there are pieces that come from, there are 4 other pieces that come from hydrostatics and hydrodynamics. And the classification, these 4 classes are non-trivial. They seem to sort of they don't seem to have any simple way of thinking about them. These 4 classes are better explained by asking how is the free energy broken up. The free energy current n mu or g mu is a vector, and it can be broken up into a piece that's along time and a piece that's transverse along space, and the piece that's along time is multiplied by scalar function, and that sort of fits here, and the piece that's transverse fits along here. Okay? So things that are in the scalar sector are actually the easiest ones to understand. Everything else turns out to be a bit harder, but we'll see how to classify them as we go along. Okay? Okay, so that's the picture that we proposed about more than 3 years ago by solving this equation, and now I'll tell you how we went about it. Okay, so the way you do this is by recognizing something that's important, that equation that I was writing had explicit diffeomorphisms and flavor gauge transformations along the thermal vector and thermal twist. So what we're going to do is go first to equilibrium and ask what happens in equilibrium, and then parameterize departures from equilibrium by by the amount of diffeomorphism in powers of those variables. Okay. So let's do this. Let's go to equilibrium and let's talk about equilibrium as hydrostatic. And I want to distinguish what you would traditionally be naively thinking of as equilibrium as saying temperature is homogeneous everywhere. Okay, that's a simple equilibrium system where the space, when all of space there is no temperature. That's not necessary, because what you can have is you can have equilibrium on a non-trivial curved spatial manifold. Okay, and you all know this. It's just that we don't tend to think of that as equilibrium. So everybody here must have solved the problem of how the temperature varies in a gravitational potential in the atmosphere. Or if you've just climbed the hill, you know that the temperature changes as you go up. It's a function of altitude. But there is no flux of energy or transport typically unless there are other gradients operating in meteorological circumstances. On a typically good day, there is no flux as you go of heat going up and down in altitude. So in a non-trivial gravitational potential, you can have non-trivial equilibrium. All you need to do is ensure that you have a time-like killing field on your background, and nothing which basically means that your fluid is not flowing as a function of that time. It's static with respect to that time. Okay? But there could be non-trivial behavior in space, so spatial gradients can be non-trivial, but temporal gradients have to be switched off. Okay? And since the diffeomorphism here in this equation was along a temporal vector beta, switching off temporal gradients amounts to having equilibrium. Okay? So here's a claim, and I want you to check this. This is a very easy thing to check. So you can take your favorite fluid system or energy momentum conservation equation, and you can study time independent configurations, which are equilibrium configurations, in the presence of a spatially varying background geometry. So okay, you can have non-trivial spatial metric, you could have non-trivial spatial flavor fields, and yet the system will be in equilibrium as long as nothing depends on time vector, which you can identify that time vector with the beta vector. So let me say this geometrically. Geometrically, what you care about is that the background sources admit the following symmetries. So our background sources were a metric and a gauge field, and what we want is a configuration where we have some background killing field k mu, which is time-like, and a background killing thermal twist lambda k, under which the diffeomorphism of the metric and the flavor gauge transformation plus diffeomorphism of the gauge field vanish. If this statement is true, then you have found a genuine equilibrium configuration. And if you found a genuine equilibrium configuration, then that system is hydrostatic, but there are spatial gradients, so there's non-trivial behavior in the energy momentum tensor. It's not just set by what the energy density and pressure are doing to leading order. So this was the insight of these folks about 6 years ago of trying to classify equilibrium data this way. Okay? Now something I want to say, which is very important. When there's one way of thinking about these equilibrium geometries, you have non-trivial spatial geometry. Okay, so in space, you have spatial gradients that are non-trivial. So you can have non-trivial curvature. You can have various departures from equilibrium, because you can have local pockets where the gravitational potential is attractive and local pockets where it's higher, and so on and so forth. What you can also have is a change of a local inertial frame from spatial point to spatial point. In other words, the way you think about equilibrium is you think about Minkowski space, and you think about temperature being same everywhere. Okay, that if you think about that as in the Euclidean way of thinking about statistical mechanics, you would say on space you have a thermal circle, and the thermal circle has periodicity beta. But it's a thermal circle that's a cylinder. It's a homogeneous cylinder over space. The circle size is the same everywhere. This is not necessary for equilibrium. An equilibrium geometry this statement here is equivalent to saying that equilibrium is described by putting your quantum system, for which you're trying to understand the fluid dynamics, on a curved manifold which has a thermal circle fibered over spatial base. Okay? So what you mean by your local temperature and which direction is time can change, and how the size of the local temperature can change from spatial point to spatial point, which is what a fibration means. Okay? All you care about is that that vector satisfies the killing condition. If that statement is true, then you can write down the hydrodynamics data in one shot. Why? Because now there's no time dependence, there's no dynamics to this problem. So you can go back to your thermodynamic intuition and say, I can compute a partition function, because it's a global equilibrium problem. In particular, if you had homogeneous temperatures everywhere, what would you do? You just write down the free energy of the system as a function of temperature. What I'm doing now is making my system inhomogeneous in space, which means that I just need a free energy vector, which is mostly a spatial vector, which is now contracted. It's a mostly temporal vector, because it's the free energy scalar contracted with the temporal vector integrated over the spatial base. Okay? And this hydrostatic partition function can be very simply expanded order by order in derivatives. Because the annoying part about hydrodynamics is classifying tensors order by order in derivatives. Scalars are much easier to classify. You all know how to do this. This is all what we always do when we write down effective field theories. We just write down how many scalars are there at a given derivative order, and off we go. In equilibrium, this is what happens here. And to show you how this works, let me demonstrate this in a simple example. So let's say we're in an ideal fluid. We're going to be at zero order in derivatives. So even though I have gradients, I'm not sensitive to them, because nothing is I'm going to look at the leading term in the derivative expansion. So I need things that are functions of my background geometry, and the only thing I have functions of are functions of temperature or chemical potential. So there's only one object I can integrate over space to write down a partition function, and that's the free energy function. Because this is now a real equilibrium problem, because we are not doing any gradients. So it's like saying you have a Minkowski space locally, and you have homogeneous temperature and chemical potential everywhere. So you have a free energy or pressure function, and from that free energy or pressure function, which is viewed as a function of temperature and chemical potential, you can extract an energy momentum tensor by varying with respect to the background geometry. This means the following. This means that the energy density and pressure that I wrote down as two independent scalar pieces of data in the parameterization of the energy momentum tensor are not independent. Because you see, if I told you this is just an energy momentum tensor, you would say, I have one scalar function here because that multiplies this tensor structure. I have one scalar function here because it multiplies a different tensor structure. But that cannot be true if you're in equilibrium. The existence of equilibrium implies that these two scalar functions are derived from some underlying scalar function, namely the free energy function. Okay? In fact, it's even stronger than that. There's also an entropy current, which is just the thermodynamic entropy density times velocity. But that thermodynamic entropy density is also not an arbitrary scalar function of temperature. It is also fixed by the same free energy function. And how is it fixed? It's fixed by the standard things you learn in your first thermodynamics class by the Euler and Clausius relations, which tell you that everything is homogeneous and the first law holds. Okay? So there's one function, if you like, you can call it the pressure function because you can trade the free energy for the pressure function, and it in turn determines everything else. So if you're trying to study ideal fluids for any system, your task is very simple. Just find what the pressure is as a function of temperature and chemical potential. Done? Do I have 2 minutes? Okay. So if you go to one higher order, it's a bit of an exercise, but it's a not so hard exercise, so I'll leave you to think about it and check. There are no terms you can write down in the partition function. Okay, the obvious things you can think of writing down are disallowed by equilibrium condition, and so there is nothing, and which is consistent with what we know. Everything at first order is dissipative. Things start getting interesting if you go to second order, and this is where I would say the classic literature ends because no one tried doing systematically higher order fluids. There were empirical attempts primarily by Israel Stewart and various other people for pragmatic reasons, but they didn't do it systematically, and therefore they missed a lot of structure. So now things start getting complicated, so let me just say it in words. So if you just count how many tensor structures you can write down for a neutral fluid, no charges at second order, you will find there are 15 independent tensor structures. It's a bit of a work to classify them, but it was done by various people, so there are 15 structures. Now you can impose equilibrium condition on them, that this killing symmetry condition, and it turns out that 7 of them will just vanish when you impose equilibrium. Okay, because in equilibrium some derivatives are 0, right? Because the divergence of the beta vector symmetrizes 0. So only the antisymmetric derivative of beta vector is non-trivial in equilibrium. So you're left with 8 tensor structures. But now you can ask, these 8 structures, like in the previous slide, have to be derived from a partition function. So how many scalars can you build into the partition function? Now this is a exercise you can enumerate at the top of your head. Because scalars are much easier to count, and it turns out there are only 3 scalars that survive the equilibrium condition. There's the spatial curvature, which of course survives because it doesn't care. There's the square of the acceleration, and there's the square of the vorticity. What actually vanishes in equilibrium are the shear and expansion. Because the shear is a symmetrized derivative, so the killing condition kills the shear, and the trace condition kills the expansion. What this means is that these 8 tensor structures are determined by 5 pieces of data, by 3 pieces of data, which means that there must be 5 non-trivial relations between these 8 possible objects that you might have a priori written down. So that's the first indication that something non-trivial is happening, that a neutral fluid is not parameterized by 15 independent transport data, but only 10 because there are 5 relations of some kind. So that was worked out by Shantanu Bhattacharya very explicitly. And if I go to charged fluids, life gets more complicated. Now you see why I don't want to write equations, because she worked this out and you find that there are 51 pieces of transport data and 17 constraints. Okay, so I think I'll stop here by emphasizing that equilibrium is a powerful point where you can try to see what's allowed, but it's limiting because it has no time variations. What we're going to do tomorrow is start putting in time variations and see what it brings us. So we'll do linear time variations, nonlinear time variations, and in fact it turns out to be sufficient to just do linear time variations because nonlinear time variations are implied by linear time variations, and then we'll be done with our classification. I'll do that and then start with the Schwinger-Kelly stuff tomorrow. Thanks.
Thank you.